Atoms are the building blocks of matter. Atoms are made up of three particles called protons, neutrons and electrons. Electrons and protons determine the chemistry of the atom. The neutrons and the protons determine the stability of the atom. At the heart of the atom lies the nucleus. The nucleus is made of protons and neutrons. These particles are further made up of quarks, which are held together by the strong nuclear force. The energy required to split a proton or neutron, and therefore separate quarks, is enough to generate new quarks. Therefore, it is right to say that protons and neutrons are the building blocks of nuclei. The strong nuclear force is both an attractive element and a repulsive element. This leads to both stability and volatility inside a nucleus. Protons and electrons attract each other due to their electromagnetic properties. Protons have a positive charge and electrons have a negative charge. Therefore, they attract. In the nucleus, the same force leads to instability of the entire nucleus. In small nuclei, such as helium, this instability is overcome by the attraction of the strong nuclear force. The two protons that repel each other are held tightly by the two neutrons inside the nucleus of the helium atom. In general, the bigger a nucleus, the more unstable it is, but this hides the whole picture. As in chemistry, there are patterns of stability and instability in nuclei, but that is beyond the scope of this podcast. For now, we will just establish that the nucleus is not a static environment and move on to explain how this explains many phenomena associated with the nucleus. Alpha decay is the emission of a brand new nucleus from within a larger one. Einstein's equation from special relativity tells us why the ejection of mass will bring greater stability to an unstable nucleus. E equals mc squared tells us that mass and energy are equivalent. Mass is simply a way of storing large amounts of energy. A small amount of mass can be converted into a large amount of energy. When nuclei are formed through the process of fusion, some of the mass of the constituent particles is converted into binding energy, which holds the nuclei together. When this same nucleus is later split via nuclear fission or a similar process, this binding energy is given back to the constituent particles as mass again. Alpha decay ejects a relatively large amount of mass from the centre of a very unstable nucleus. An alpha particle is the nucleus of a helium atom. To create this mass from energy would require a large amount of it. For this reason, alpha particles come from the largest of nuclei, where the interaction between the repulsive forces of electromagnetism and strong forces and the attraction of the strong force is not balanced. The forces are dynamic, meaning that the nucleus is in flux. The imbalance of forces generates accelerations within the nucleus, leading to strains and tensions within the structure of the nucleus. Because of this fluidity, we can imagine the internal structure of a large nucleus as a turbulent fluid, where more stable mini-nuclei exist. The most stable of nuclei are those of helium. It requires a large amount of energy to break up a helium nucleus. You can imagine the turbulent internal workings of the energetic large nucleus as a soup of helium nuclei flying around, being pulled backwards and forwards by the forces inside the nucleus. The energy inside the large nucleus is enough to expel a helium nucleus, but we do not know when. The inside of the nucleus is like the inside of a bingo machine. All the balls are bouncing around with a lot of energy. We know that one of these balls will come out of the nucleus. We just do not know which one or when. This leads to an inherent uncertainty of nuclear physics. The system is so complicated that we cannot tell when a nucleus will decay, just that it will at some point. The next form of radioactive emission is beta decay. This is still the ejection of a particle, but a much smaller particle. The particle in question is either an electron or its antimatter equivalent, the positron. This particle is only subject to the electromagnetic force due to its charge. This form of decay has nothing to do with the stability of the particle emitted, and is a completely different mechanism for energy loss and stability increase of the parent nucleus. Beta decay is a mechanism in the weak force family. The weak interaction changes the nature of a quark within the nucleus from one type to its twin. For beta minus decay, we see a down quark changing to an up quark and emitting an electron. For beta plus decay, we see the reverse. An up quark turns into a down quark and emits a positron. In both of these situations, you see a change in charge of a whole unit. For beta minus, the down quark has a charge of minus 2/3 and changes into an up quark of charge plus 1/3. This is a step up in charge of a whole unit. It gives off -1 charge and so an electron. The reverse is true for beta plus decay. The whole reason to do this is to rebalance the forces within the nucleus. Beta minus decay tends to happen when there are too many neutrons in a nucleus, and therefore the strong force is too strong. Turning a down quark into an up quark gives a better balance of quarks within the nucleus, and has the added bonus of giving off a little energy in the form of a beta particle. Beta decay tends to happen where the parent nucleus is unstable, but not hugely. The nucleus is not about to rip itself apart. It is more likely to simply rearrange its internal structure. It is like a pile of very heavy stones shifting to pack more tightly together. You can see that the pile of stones will eventually shift, but you cannot tell exactly when they will shift. So again, the emission of a beta particle cannot be predicted. You can say that it will emit a particle, you just can't say when. The last form of emission is gamma emission. This is simply a type of energy given off by the most stable of our unstable nuclei. In the same way hot objects give off infrared radiation, unstable nuclei give off gamma radiation. Gamma radiation is energy and not mass, and so a gamma wave emission removes less energy than an individual beta particle emission or alpha particle emission. Gamma radiation is given off by even the smallest of unstable nuclei. As with the first two forms of radiation, gamma radiation is also unpredictable. You can see the instability of a nucleus that will radiate a gamma wave, but you cannot say when it will give off that energy.